Today's training will focus mostly on the structural software Midas Gen. We're going to cover actually 3 different structures, and we're going to go from everything from footing design to pile raft design to wall design, basement wall design under various loading conditions. So we'll cover special boundary conditions and special load conditions for these kind of substructures. And in the end, actually, I'll show a link for this structure to our other module and gen and how we can even extract the plan and horizontal drawings of the whole structure itself. So as I mentioned, we'll cover 3 models. We'll first do a simple footing design. We'll then pass on to the pile raft analysis and design. We'll do the rebar design of the piles. And then lastly, we'll do the basement wall analysis with some hydrostatic and earth pressure loads, as well as the design of these reinforcement, the rebars of the wall, basement walls and the raft. So starting off with the footing design, these are the dimensions of the model that I'll be using today. So in order to save time, the models themselves will already be created. We've done previous trainings where we cover all the importing CAD files or modeling from scratch. So at this point, this could be considered more of a specialized training where we're focusing on just special boundary conditions, loading, and then the design on some of these substructure like footing or piles. So the model that I will open in a second already has the following materials sections defined and assigned. So as you see, we just have concrete structure for this case with a few beams, girders, and columns defined. And there's a wall thickness. So this will be the file that I'm about to open, and basically we'll just be missing the boundary conditions and what would be then the design itself. So we notice that we also have loads applied, and this includes some response spectrum analysis. But as I mentioned, we have already covered this in previous sessions, so we will skip the part where we add the loads and we'll straight into what would be the boundary conditions and then analysis and design. So let me go ahead and open the start file. So this is Midas Gen. As I mentioned, we have the structure already in place. Here in the work street, we can see the materials, the sections, and even the cases for the loads. So we have floor loads and some beam loads and then some wind loads, everything applied already. What we don't have defined yet is the boundary condition. So this is what we will be first applying to our model, and then we'll jump right into the analysis. So for the footing, we'll go here to boundary, and we see we have different kinds of boundary conditions we're going to apply. We're going to start off with the most simple one, which would be just applying fixed supports. We go here to supports, and here you can select the degrees of freedom, either being displacement or rotation, that you can fix. And you can do any kind of combination that you like, depending on what it is you're trying to model. We have some views down here for how to view the structure. And actually, one of these commands allows you to see the sections assigned or just as they are in elements, which in this case are line elements. It makes it a little easier to select if we just have the hidden view. I'm going to do what would be, doesn't matter if it's the front view or the side view, but what I do want to be careful on is just selecting, by drawing a rectangle, all the nodes in the bottom. So you see here, if I do one of the side views and just draw a rectangle, all the nodes are selected. So when I click apply, I see my fixed boundary condition set. So for this, as I mentioned, everything is ready. We're going to jump right into running the analysis. And it should take a few seconds, given that the structure is very simple. So we see here it's done. It took less than 3 seconds to run. So we can go look into the results. We go here to results. We see that they're grouped up, so we can see deformation or forces, reactions. So let's take a look at some of the deformations. We see in this case that we have different load cases. The first 8 or so are directly the load cases we have created, while the rest, let's say CB, are load combinations that you can specify by going here and you can create automatically, auto-generate by different norms. In this case, we're using the site code ACI 318-2014, and it'll create the combinations for you. As we'll show, you can also make your own combinations. And this is also for footing design. In this particular model, we also want this to be generated. In this case, they're already generated. But these are the load combinations used for the design. So let's take a look at the results, I don't know, for the live load case. So you can select here for live load case, and you can click kind of deformation or displacement in any direction you like. You can activate here the legend. If you don't want to see them in exponential format, you can go here to this icon right next to legend and just say it's fixed. And then, of course, you would have to change the units. In this case, down here, we can do something smaller like millimeters. We can there activate the hidden view just to make it a little more clear. Or you can do inches or whatever. It doesn't matter. After you run the analysis, you can change the units to any format you like. So we can also take a look at other things like the forces or the moments. So we can change here either from this tab or from this tab on the work stream and just select the beam diagrams. So Fx would be the forces. We could tell it here to do a solid fill of the diagram. So here we're looking at the forces for the live load case. My would be the moment, or the moment about y, because you can also do for the other direction, C. So here we're looking at the moment. And other things you might be interested in, for instance, might be the reactions. So let's look at the reactions for the three directions under the same load case. So there we're looking at the reactions. So you see for some of these columns, or in this case, this column at the bottom will have footings. This gives you an idea of what some of the load case expectations are. So we already created the load combinations. So that means we can move straight into design. We'll go here to design tab. And we're working under concrete, so we will click on this tab here. You see that we have different kinds of design. You can do steel design, concrete design, steel reinforced concrete, all kinds of sections. So we're going to stick to concrete. And here in this column, we'll go to the very last option, which is for footing design. So for footing design, you have two options. One would be the auto design, and the other one is first you can tell it to do a code check. So we'll start off with code check, and basically what this means is this allows us to select any node of interest. So let's pick this critical node in the middle here, and I can actually activate the node numbers displayed. So we see here that it's node number 20 that I've selected. And what I can do is I can give it some preliminary information about like the rebar that my current footing has, the dimensions of my current footing. So let's just say currently what I had in mind was a footing of 1.5 by 1.5 by 0.35 meter with the rebar distribution of bar number 4. You can give it, because it's footing, you have to give other information about the allowable soil pressure, if there's any surge charge, and information about like soil density and such. And so you can tell the program then to do a check based on the selections you've created of the combinations of loads. This will pop up and allow you to select load combinations. And once it's created, you will get this kind of report. So we see that it passes some of the requirements by the current dimensions, but it does not, in red, as it shows NG not good, what would be the requirement for the pressure, the soil pressure, soil bearing pressure. It's generating almost twice as much as what we specified can contain. So the footing will need to be larger in order to sustain this kind of pressure in terms of dimensions. So what we can do is we can tell the program specifically to design it based on all the information that we've given it. And now when we do auto design, the program has determined that your footing should actually be of 2.3 by 2.3 by 0.4 in terms of dimensions. So it's a different size of footing, but we get this kind of report, and now we see that all the loads or all the checks pass. So this is how you would do a rebar and footing design using -gen. Again, very simple case for fixed boundary conditions. So we will now move on to, well, this is what we just finished covering. We will now move on to what would be the Palrap model for analysis and design. This is these are the dimensions of our current, of the model we're going to be working with. So we have the structure that's around like 10 stories or something, 22 meters high, and we're going to create the piles that will be 10 meters deep all along where the locations of the columns are. Again, the starting file already has the sections, the materials designed and assigned. However, what we haven't created yet are the piles and the raft. So we'll be starting off with this model, and we'll go from here. We notice, and we'll see this also when we open the file, that in the worksheet, the pile sections and the thickness 0.3, which corresponds to the raft, are in blue. That means they have not been assigned yet. So this is kind of what some of these descriptions mean in the program. So let's open up the starting file. So as I mentioned, if I expand here on sections and thicknesses, we see that the pile is blue as well as the thickness of the raft. So we're going to go ahead and start by creating the piles using the command extrude. We'll go here to element, and we can see we can create elements, copy, merge, intersect, divide, whatever. We're going to use the command extrude. We're going to use the method node to line element, and here's where we select what material and, more importantly, what section, which we want to select piles, will be used. And then we would just give it a basically coordinate direction, global coordinate direction. So we would say it's going to be down. And we can do it several ways, but let's say it's going to be 10 meters, but we would like to have a node at every meter. Basically, we're dividing the pile up into 10 sections. So this is why I'm telling it 1 meter down 10 times. And what I would do then is just carefully select what would be the location of these piles here. So I try to select the nodes that correspond to where the columns are. So I want to zoom in with my mouse just to make sure. So only where the where the columns are. And that seems to be all of them. I can kind of just give it a quick inspection, and then I would just go apply. And we see there now, if I activate the hidden view based on the sections, that we can see that these are piles, different section than what the columns are. So I have my piles in place, and I can now move on to the raft. So what I'm going to do is I'm going to use a command called AutoMesh to mesh my 2D raft. I'm going to do the hidden view again. And so I'm going to do it by the line method. So I'm just going to select the beams on the, I guess, ground floor, and that will be the guide, the boundary for my raft. Here will be a plate element. I give it the material, and the thickness of my raft, as you recall from the table, is going to be 30 centimeters. So I would just do a side view and draw a rectangle to select the line elements at the base, and just go to apply. I might have selected something else. So let's go. There we go. So we see here now, just be careful to make sure it's only the line element on your plane. We see now if I activate the thickness, we have our raft and our piles created. So that's how you can create some of these substructure sections. What we're going to do next is apply the boundary conditions. So in the last simple model, we just fixed the columns, and we assumed it was just the footing design. However, for more advanced cases like where we have piles and rafts, Gen offers advanced boundary conditions like soil springs. So we can specifically select some springs for the piles and then some different ones, surface ones, for the raft. So let's first apply the soil springs to the pile springs. We see here, well, we're basically modeling the ground as springs in different directions, including the tip. Midas Gen has its own internal PY curves that you can select from. So let's just stick to sand. The ground level at this case actually is the raft. This is the global coordinate system. So ground in this case is 0. But you can give it whatever value. You just have to specify whatever your model is. The diameter we know from our list to be of 0.5 meters. And then this is just information that you would get from your, I guess, geotech team or from the lab. Information about like the unit weight of the soil, the earth pressure coefficient, and what would be the coefficient of subgrade reaction, friction angle, and more or less if it's whatever condition you have, initial condition. So we would then apply these by selecting the piles. What makes it easy is instead of trying to, you could select from the view and try to capture your nodes. What you can also do is from the work stream, specifically single out a section. You can use a second work tree by right-clicking on this corner and activating this. So you can select from the second work tree any section you like. So you can just tell it, select the piles automatically. And so we've applied the soil springs to the piles, and then we would go on to surface spring, and we would repeat a similar procedure for what would be the raft. So here we see that we would apply the same conditions, less information, but basically what we need is the subgrid reaction in the 3 directions now. So we will use this rule of thumb of the kx and the ky being 10% of what the subgrid reaction is in the vertical direction when it comes to these kind of flat rafts. But of course, you can use, if you have more information from the geotech lab, you should ask them which coefficients to use for the different directions. So here, again, we can just select a side view to select the nodes in the raft, or we can specifically just select from the work street the one that corresponds to the thickness of the raft, which we know is the 30 centimeter one. So now we have the boundary conditions applied. And before we run the model, because we've created additional information in terms of the stories, we have piles now. So the model is now much different in dimensions than it was originally. We would have to tell the program information about the stories generated, since the piles are also considered basement stories. So up to this point, the program was just, all I knew was that at the basement, at level 0, that was the lowest point of the model. We wanted to auto-generate, basically to consider all the additional nodes in the pile direction, in the negative direction. So we can just select everything and basically tell the program that consider these piles that are below ground as well. So now we can just run the model. It was also in that story data where you can control if the program would consider the floor diaphragm at each floor, and you can manually activate or deactivate. So here it's almost done running. And it's completed. Took a little bit longer. And again, we can look at different results like the displacements. Again, it can be under some sort of live load, or we can do a little more interesting, perhaps. Again, we had the same kind of response spectrum condition that we had shown in the previous model. So you can look at any load combination that you like. So here we're just looking at response spectrum and X, just as a random choice. And again, for displacement results, it's a little more clear. If you activate the hidden view, you can show the thicknesses of the sections. And then you can change the units around to make it a little more clear if you like. You can then, also look at some beam, other things like the beam diagrams that we saw. So axial forces, or moments. And now we'll go to the part where we design the pile reinforcement. So for that, again, you need to create load combinations. For concrete, you would go here to load combinations, auto-generate, and you would select the design code that you want to work with. So we updated it to the most recent for the load combinations. And then we go here to design. Again, we're working under concrete, reinforced concrete design. So what we have to tell the program before it can run the check or the design itself is it needs rebar information. It needs to know how the rebar are distributed within, in this case, the piles. The program considers piles to be column sections. So you would go to modify column rebar data, and here you would find all your sections that are considered columns, as I mentioned then. So you would just select the pile and give it some initial condition or initial information about the size and distribution of the rebar. So let's just say that initially it has the following kind of rebar distribution. And basically I just had to go to add replace. It was a little, you go to add replace at the bottom and you see that now we have a confirmation here. So we can actually now run what would be a column check in this case. So first we wanted to check to see if the current rebar we gave it is sufficient based on the load combinations. So we would go to, again, RC design, and this kind of column check, since the piles are considered columns, and you can see it in the image that they're in red. So they were already selected because we were assigning the rebar information to it. So by doing this, we're focusing the program to only worry about the design of the piles, not all the columns. If we don't select anything, it will just do all the columns in the program. So first it's going to do a check, and it's going to give us a list of ones that pass, who are okay, and ones that don't, which will have an NG and it'll be in red. So here we can expand this, and we can look at individual members. So we see some are okay and some are in red. So we can make this a little easier and just tell it to show us the ones that are not good specifically. And we can also specify, I'm going to let go of the current selections here. We can even tell it to point it out for us. If we activate this option, connect to model view, if I select it, I should be able to see that only one of the sections of my corner pile is the one that's not passing with the current distribution of bars. I can get a little bit more clear detail of that if I go here to graphic. It'll give me this kind of report, including the PM interaction diagram. So it's basically telling me that it doesn't pass actual force and moment capacity checks for the current bar distributions of six number 4 bars. So I can just tell the program directly to go ahead and do the design. of the current section. Actually, I would have to go to code design, column design. So this is the one we had. And now when I go to recalculate, we see now that it's in blue. And if we place close attention, we see that now the rebars, it's saying that you should have 10 number 5 rebars. I can take a look at that graphic again with the new distribution. And so we see now that the rebar distribution has changed, it's been designed, and now all the checks pass. So here's your PM interaction diagram. You can also get a 3D PM, so for both moments, directions for the specific member. So you can kind of get these kind of advanced reports, and then you can just tell the program to go ahead and update the rebar data in your section, so that if we were to go back to the original rebar data, we see now that it's changed to the recommended. So that's for pile raft design, the design of the piles. And lastly, what we'll be looking at will be the last model, which will be, this is what we were doing, the design and the rebar. The last one actually will be basement wall analysis and design, and we'll actually also look at the raft and how to do the design of the rebar for the raft and the walls. We'll do both. So this is what the model looks like. We will be similar sections for the top part, but the substructure now will also include basement walls, meshed elements, and a bottom raft. So our basement will be about 5.6 meters deep, kind of like about 2 stories of what the regular upper structure is. And again, the sections, everything else has already been assigned, the loads have already been assigned, but as you notice in our starting file, what we haven't created yet are any of the substructure. We don't have any of the basement walls or the basement raft. So I'll open the starting file and we'll go from here to creating these substructure parts, including what I guess could be considered piles, but they're actually will just be underground columns, again, by using the extrude command. So this is the starting file for the basement wall structure. So if we get started, we're going to extrude the location of the new columns for the basement. We'll go to element, extrude. Again, we'll do node to line. The material will still be concrete. And this time there are no piles in the sections we can select. So we'll just, I already know that this is the dimension for my columns. So you would just click the section of whatever thing you wanted to create. And this time we're going to tell it that we want it to be 2.8 meters 2 times. So we're only dividing the columns up into 2. And so I then carefully, just be careful here when you're about to select something on the screen that the program might actually also think you're just trying to tell it a distance directly. So here I just go on and select the location of my columns, similar to what we did for the piles. And additionally, because we're going to have walls, let's extrude the nodes at the corners as support for the walls. And I'm missing one right there. Oh, wrong one. Okay, so we have the columns and the corners selected, so we can just go ahead and apply to create the extrusion of my sections. So now we have the columns for the substructure in place, as we see here, and we can see that division in the middle. What we're going to do now is we're going to create the walls, the basement walls, and for that, again, we're going to use the AutoMesh command. Last time we used line elements. This time, as the method, we can do it differently. We're going to use the node method. We select the material. The thickness of the wall will actually be 20 centimeters, and then in the end, we'll do the raft at the bottom. And so what I'm going to do is I'm just going to select corner nodes to create rectangles for each wall. What I want to do is I want to be consistent. You see that as I'm clicking each corner, I'm creating a rectangle. I want to make sure that each corner is actually selected so that it does look like a rectangle, and that I'm doing it in the same direction every time. So I went counterclockwise. So in order to keep the, I guess you could say, local axis directions consistent for the walls, so that when you apply boundary conditions and loads, positive is always in outward or inward normal force or normal direction, you want to keep doing it in the same direction when you're meshing these elements. So I'm consistently going counterclockwise when selecting the four corners. There I selected one too soon, so let's just start again. And then the last wall. So we have meshed our basement wall, and now what we want to do is mesh our raft by this other method that we've just been doing. Only difference now is my thickness is going to be 30 centimeters for the raft. So I just click again on four corner nodes. I can actually rotate my model as I'm selecting the corners. And just go to apply. And so we show the thickness. You can kind of see different colors assigned to the different rafts and walls. They're still shown as 2D element flats. You can actually control that in the display option of the program. If you go to draw, hidden, you can tell it to show you the frame and the plane thicknesses of your sections. So it looks a little bit more like the sections assigned. So now that we have the raft created, we can go ahead and apply the boundary conditions. For the raft, we're going to do something similar to last case. We'll just select the surface springs and give it subgrade reaction, the modulus in each direction, and we'll do the rule of 10% in the XY of whatever the vertical is. And I basically just select the raft, bottom raft nodes. For the walls, however, I'm going to actually only activate the walls by selecting here thickness activate from the second work tree menu. So you see it's a little handy for these kind of conditions too. Just to double check, I'm going to take off the thickness, I'm going to put the top view, and I'm going to activate here on display the local axis of my nodes, or of my element. So we just want to make sure, in this case, that the positive C, the normal direction, is consistent, so it's outward. So we are going to apply a compression-only spring to the walls. And so here is where this becomes important. We want it to be consistent, and so we're selecting direction to be in the positive normal of these springs. And for here, we would only give it the modulus of subreaction to be the same. And so we actually just go about and draw rectangles to select all of our wall elements. Actually, what we need to do is do these one by one, since they have different directions. So I think you can just do each axis like parallel, but let's just do one by one, just to keep it easy, like that, like in sequence. And make sure you're selecting only in a single plane, like this. So we've now applied the soil springs to the basement wall, and I would like to undisplay those here. You can first tell it to display and then undisplay. Okay. And what we're going to do now is we're going to apply the special load for these kind of basement wall conditions, which falls under hydrostatic pressure. So we have created two load cases, two static load cases, one for what would be the water pressure load and another for the earth pressure load. So let's do first the water pressure load. We see here that the program internally has its own distribution where you just have to give it information like where the reference height is, like 0, starting point, so that would be this point. And then you have what would be called here the constant intensity. So this would be like a surcharge. And then the gradient of intensity would just be the density of your, I guess, whatever's creating this load. In this case, it's water. So we can change the units to kilogram force per cubic meter, and it would be 1,000. And from there, we would just select all of our basically basement wall elements. So in the PDF of the manual or of the tutorial, we include a distribution or an explanation. So if we were only doing water load, this would be the only thing you'd have to do. If there's no additional surcharge, you would just basically give it information. Oh, and you give the gradient to be negative. For, if we wanted to consider, let's say, the structure is completely offshore or some special condition where there's only water. And you see here the arrows pointing in the application of the distribution, so we know it's correct because we want the pressure to be from the outside in. If it was a water tank, holding water tank, then it would be in the opposite direction. Well, that's just showing you, in case you wanted to have this kind of condition where you were considering only a water pressure load. Let's do now, we'll use the same function, hydrostatic pressure load, for the earth pressure. And in this case, there's a little bit of different rules to follow. So it would be considering the lateral soil pressure, and you could do it different ways. So if you only wanted to consider the soil without water, you would then consider what would be the density, unit density of your soil as a dry section and multiply that by some sort of earth pressure coefficient. So let's just say for this case, we're using an earth pressure coefficient of 1. I think in the previous model we used 1.4. So again, that's information relative to the site. But you multiply these two to give you what would be the intensity. And then whatever surcharge you want to consider, surcharge pressure you want to consider, you would also apply that. However, if you wanted to consider both, like a groundwater condition of, you would have to create these separately. So you would do the water density as we did in the previous case, and your soil would be the density of your soil when considered wet, if you will, like with water. So for this case, let's say we are in sand, and we have the following density, unit density, and then the coefficient is 1, and this is the surcharge. So we would be applying these kind of condition as we see here. So the constant intensity would be the surcharge. We're saying that's additional charge on the surface. And then the gradient intensity was our density multiplied by the earth pressure coefficient. So that's how we get to these values. And this will be the only load we'll be looking at for results. But you can do any kind of combination that you deem necessary for your design. The program does give you different options. So I'm just making sure that this is under the earth pressure loading condition. And we have this feature here where it allows you to select anything that was last selected. So this is kind of handy for these kind of loads where we're applying a different load to the same elements. And then from here, you could do the load combination. And if you wanted to, you can manually add a load combination related to the distribution of the water pressure. You could say something like a certain fraction based on maybe the Boyd ratio, and another one for the dry earth, or as you know, in our case, we already consider the earth pressure with the water being considered into the density. So it all depends. Just keep track of what it is you're modeling when you're applying the loads, and keep it consistent so you don't like have the water twice or so. So from here, the last thing we need to do is just let the program know about the new sections, the story data. However, here it seems it's already recognized that the basement floor is at 5.6 negative meters down. So because there's nothing else in between, we don't need to update anymore. It's sufficiently updated. So we can just go ahead and tell it to continue, because we don't want it to consider all the nodes along the basement wall. So let's activate everything and quickly move through this. Again, we've already seen the results for where the displacements are, the deformations you can get for that, the forces you can get. So we've been looking at beam diagram forces, but you can also get this kind of results for the plates, which in this case would be our walls. So let's just say we want to see the most important case in our case would be the earth pressure. And we can get results for the max forces due to this load. And we can change the units to any kind of units you like. What's also interesting for these kind of models where you have rafts and walls is you can also get results like soil pressures for different directions. So we see this kind of soil pressure here under this condition. And so the last part I'll cover here will be just the design itself of the rebar for these meshed elements. So now we're looking at mesh design, meshed slab, meshed walls. So we'll go first here to mesh design, and we have to specify to the program which load combinations to consider. So you can select whichever combinations it is you want for your wall, and depending on the different method you're going to select for the slab or the raft. Secondly, we also have to specify information of the rebar criteria for design, and then we'll do that once more for the check. So you give it information about the size of the rebar. You can select from any kind. You can activate these different options and select different rebars that you want to consider for the design. So this information I specify in the PDF, but again, it's what will be used as the design criteria for what would be slabs or mats. As well as the wall. And then the last thing is, before we do the design, we wanted to check as well. So that would be, so we have design for criteria for design and criteria for check. So here I would select from the second worktree my raft section first. And I'm going to tell it information about how the rebar is distributed. So we're going to tell it that initially it has number 3 bar rebars, and there's a small map that kind of gives you an idea of distribution and directions of the two. So you go to select the elements and you go to add. You have to give it a name. And then we do the same for the wall. And we give it information about this. So again, number 3 rebars at 100 millimeters spacing. And so now we would be able to run the design. So we go ahead and go to mesh, and let's first do the slab. So we'll do the flexure design. And we have different methods of selection. We'll do it by rebar. So the manual actually clarifies what the different conditions are, if you were doing resistance ratio or word armament design, which is one of the programs to do the rebar design. So what we would get is this kind of colorful map, and it's basically telling us the sections that have different bars at different distributions. So we see that in red we have number 5 bars at a different distance than in the blue or green. And so this is the program designing for us the reinforcement of the slab. So you can just go to update rebar, and if you go back here to the slab criteria, you see now that these sections have been updated, and you can, if you wanted to modify, you can go here and give it this information about, or it's giving you the information of the distribution. And so the last thing would be to do the same for the wall. Just go to wall design. Again, we'll do rebar. Wants to make sure that we've given it information about the rebar checking data. And it would tell us here basically that some of these bottom corners, we need a certain kind of size of rebar spacing. And the rest in blue is fine with the other spacing. So it's the same thing as the raft. So that's how you can design the reinforcement of your slabs and your basement walls using Midas Gen. The last thing I'd like to show you is how these programs communicate with each other. For instance, with the new module that we have, Midas Engine, which is very handy for things like drawings. So what we're going to do is these programs communicate. I'm going to export this structure, this basement wall structure we've been working on for Midas Gen by going here to exporting, just creating the MGT file, which is the one that I can read in Engine. So literally you just have to go here to menu, export, Midas Gen MGT, and just save it in some file folder that it's easy for me to find. So I would just export it and then open up, this is Midas Engine. I would just go here to import MGT file and open this model up. It might take a second to import. So for time's sake, let's just say I have what the model would look like had I also, let's say, finished running the analysis. So it would import the sections. We notice that this is geometry that's not meshed yet. The Midas Engine is a little different. We mesh right before you run the analysis. So this is when we go to the post processor, we can actually see now the mesh distribution. And so here, like for instance, if we're looking at the results for the earth pressure set, this is how you can see the results, and you can activate the deformation. So it's very similar in terms of how the result, well, actually the results are shown or organized in a little bit different, but it's very intuitive. So they're just set by grouping. What's good about this program as well is the advanced CAD features, even in terms of what it can export or create in terms of final. Let's say you have the final drawing, final dimensions, final design, and now you want to do the drawings. So you would have just give information about the story data in the program, which again can be auto-generated. In this case, we're just verifying the height of the file of the basement and the structure. And what you can do is you can link this to what's Midas drawing. Which it's open in my other screen. Let me show this other screen real quick. So what you would see is the program automatically opens and it gives you this bar of information as the drawings are being generated. It's pretty handy in what the final drawings can be, because it can be for each story, or it can also be like cross sections. You can even generate like a bill of materials. So it's about a third of the way done. That'll be maybe another minute. And so when it's complete, it allows us to generate the following kind of drawings, be it of a single story or several stories, as well as cross-sectional parts of your model. And so to generate this, you would go to drawing creation. So you could do structural plans, and you would specify which floors. Let's say here I selected floor 2 and floor 4. And you would get these kind of drawings that you see, the two on the bottom. So you have these for the different stories. And then what you can also do is generate cross-sections of your whole structure for the other views. So you could go back to drawing, and you can generate these cross-sectional layouts. And you just specify to the program first a name. You go down here to enter on the bar. And then you select like a starting point, an end point of something crossing the data. You go to enter. And you can generate these kind of cross sections of where. Let me try one more time. So you can select any of the floor plans you like. You just have to make sure you cross everything, and then give it a direction of this of what you want the section to be crossed. So I just basically went a little bit upward. And it'll give you this option of where to lay out the next drawing, if you will. And so you see here I have different cross sections. You can see where this is the first one I generated and this is the second one I've generated. So you just have to be, you can generate multiple ones as, you know, the structure itself is going to cross through different parts. So in some of these you're including the columns and in some of these you're not, based on where you drew this. So it's a handy feature of the drawing aspect of it. And there's other things you can create with it as well, including what would be like a volume output. So this would be the equivalent of what would be a bill of materials. So if you were to generate that list, you would get an Excel sheet. Here's where you can activate what you want to consider in this. And it would generate an Excel sheet with the volume of the concrete or steel or whatever section you had. So here I'm just loading the Excel file. And you would get this kind of Excel sheet where you have all the sections in your model, as well as like the total. And if you add information about like the cost, you can have basically a bill of materials kind of thing. But that would be the conclusion of the demo in terms of how these programs interact and how you can do the design of some of these sections. I'll now have the presentation passed back to Daniel. He has a little bit more to share about these programs. Thank you.
Thank you, Angel. Like Angel said, Midas is very powerful.